shows how good the brain is. We know that the future of neurological research is almost impossible to predict. However, one thing is very certain, and I say this with feeling, we are on the cusp of a paradigm shift that will have significant impact on the prevention, the treatment, and hopefully, down the line, potential cures of some of our brain diseases. That's pretty exciting. And what we can really look forward to, first, that there will be an increasing understanding of the basic operations of how the brain works. I just want to reflect for a moment that inside your head you've got a little universe. And that universe consists of 100 billion nerve cells in the brain. Now what's 100 billion? Well, there's about 9+ billion people on Earth. So if every one of those people was a brain cell, you'd have over 10 times the number of people in Earth in your brain. And that's the reality of the complexity of the brain. It's incredible. Even more incredible is to know that we have just as many what we call glial cells, which work in closely with those brain cells. And we have over 10,000 times that number of synaptic connections between the brain cells, plus over 40,000 genes and proteins in each cell. So you can sort of get a bit of a feel that understanding the human brain is a challenging task. And that's why I use the term the universe inside our head. I first saw that sign when I was in Boston. And on the Science Museum, walking across the bridge, was this logo, and they had a special symposium aimed on the brain. And they called it the universe inside our head, and that's exactly what it is. Despite the challenges of the complexities of the brain, we are moving forwards, and we're added enormously by the unpredictable but inevitable quantum leaps in new technologies and new therapies. And these therapies have underpinned so many of our breakthroughs and different technologies in neuroscience to date. I'm proud and I'm very humbled to say that many breakthroughs have been aided by brain scientists here in New Zealand. I say aided because it's a collaborative term, you see. We all work together, and you get the feeling tonight as we hear from our distinguished guests, speakers, that nothing happens without teamwork and without collaboration. So we're actually seeing a revolution in brain research through being able to visualise the brain in action in all sorts of ways. So this is occurring at the level of both single neuron and populations of neurons through fancy laser microscopes, as well as at the whole brain level through techniques such as functional MRI. And even more recently developed technology sweeping the neuroscience world is the genetic encoding of light-sensitive proteins in nerve cells, so that fibre optic light impulses can be used to control their activity, even deep within the brain. And this is going to offer us huge opportunities down the line, not only for research, but probably for treatment as well. So that expanded use of technology is going to push us into a new era of understanding how the brain works. It's fantastic and makes coming to work each day so very exciting for all of us here on the panel. What about the future treatments for brain damage and disease? And this is an area which is so very critical to people affected by disorders of the brain. While cures will never arrive fast enough for those in need, there is good reason to be greatly optimistic that help is on the way in all sorts of forms. For example, in Huntington's and Parkinson's, Alzheimer's fields, and for many other neurological disorders, good new ideas are increasingly being tested in clinical trials. Moreover, there are other promising new lines of research, such as ones that harness the cell's own natural defences for combating damage. Prosthetic brain machine devices for restoring function, and nanotechnology for delivering to the brain the new therapeutic chemicals being designed by modern medicinal chemistry. Here in New Zealand, we have begun to culture live brain cells directly from excised tissue, tumour tissue, and other tissue which has been excised at operation. And by culturing brain cells, we can learn how brain tumour cells, how different types of diseases affect brain cells, and we can then develop in the lab using human brain cells technologies and methods to actually target them with trial drug compounds and our very own immune systems. It's opened up a huge frontier. As these and other new treatments ripen into mature research streams, the door to effective therapies begins to open even wider. On other fronts, neuroscience will increasingly be used to address brain problems typically thought to be in the realm of psychology and psychiatry. Developmental disorders such as ADHD, autism, and schizophrenia are known to arise, at least in part, from brain trauma or dysfunction very early in life. As the cellular and molecular mechanisms that underlie these disorders become better understood, there will be a convergence of neurology, psychiatry, and neuroscience in devising new therapies. Aided by emerging new technologies such as those which I've just described, we can expect that these therapies will combine with modern psychological and psychiatric interventions to give much better outcomes than are currently possible. And that's exciting for all of us involved with research who want to actually help people who are touched by a wide myriad of brain diseases. Neurodegeneration brain disorders are on the rise because of our aging population, but they remain elusive to understand and to treat. And when we have a good idea, a reasonably good idea of the underlying cause, such as an Alzheimer's and Parkinson's, a major hurdle is that it's not possible to specifically treat damaged tissue without causing unwanted side effects on normally functioning parts of the brain. That's a challenge. This issue is particularly challenging in the future. We'll see much more research aimed at realising the potential of stem cells, of gene therapy, deep brain stimulation and new drugs as viable and specific therapies. And we're going to discuss some of these exciting areas tonight. If there's one certain feature of the future, it is the need for more research and thus more funding to turn hope into a real reality. So it's a special privilege for me tonight to tell you that the Neurological Foundation Council approved over $1.2 million of brain research funding in its second grant round of the year. That happened today. Fantastic. And there's going to be music to my ears and music to all the researchers here. Thank you so much. Thank the Foundation. So we're so grateful to the Foundation and to all its supporters, many of you here tonight, all of you here tonight, I hope, for your continued support and commitment to our work. So this has never been a more exciting time in brain research than now. Tonight, I'm incredibly honoured to join 4 of my research colleagues to share with you the remarkable progress we are making. We are so privileged that these 4 international brain research pioneers joining us tonight are members of our Centre for Brain Research Scientific Advisory Committee. Now they've come in from all the corners of the world, as you'll hear soon, and we've kept them pretty busy. They've been meeting over the last 2 days to review our research, looking at our progress to date, giving us ideas about deciding new directions that we should go in the future. And it's been a marvellous time, and thank you very much for all your contributions. Collectively, it's interesting, the 5 of us on the panel, and I did the sums very carefully, We have over 200 years of research experience, but we're very young.
Dangerous number.
And we all feel young, and that's the you've got to keep the brain young, you've got to keep stimulating. Stimulation is what it's all about. So, you see, our panelists come from London, Zurich, Boston, Brisbane, and I'm of course here in Auckland. We work very closely to move the frontiers of brain research forward in all sorts of ways. And the collective wisdom and scientific expertise you see in front of you now, amongst the 4 overseas people, covers a wide myriad of brain diseases. Together our research teams are shaping a path to a much brighter future for people and families affected by neurological disorders. Achieving tangible benefits for patients, whether treatments or rehabilitation, is the driving force behind everything we do and in all our work which we love. So ladies and gentlemen, it's my incredible pleasure to welcome Professor Anne Young from Harvard University, Boston, Professor Hans Muller, University of Zurich, Switzerland, Professor Chris Shaw, actually a New Zealander, just pulled him back home for a while, from King's College in London, and Professor Perry Bartlett from the Queensland Brain Institute in Brisbane. Thank you all for coming. Thank you for joining us tonight. Our very special chair who's going to keep us all under control is Sue Giddings from the Neurological Foundation. Sue.
Thank you, ladies and gentlemen, and welcome. I hear through the grapevine that there was a late night last night with my colleagues to my left, and it ended up with a big joke-telling game, and we're going to start this evening with a joke, actually, in very good taste, from Professor Anne Young.
So I'm from the United States, and I am a neurologist. And I heard 3 surgeons talking to each other about their surgical prowess. The first surgeon said, a concert pianist came in to the hospital and 3 of his fingers had been chopped off in an axe accident. And I sewed them all back on. And last week he played in Carnegie Hall. And the second surgeon said, "Oh, that's nothing. I was called to see a man who had gotten caught in a revolving door, and his arm was severed and both legs were severed. But I was able to sew them all back on, and he is now an Olympic runner." This third surgeon says, "That's nothing." He said, "I was called to the emergency room because a train had hit a man on a horse crossing the tracks. And all that was left was the horse's ass and a shock of blonde hair. I sewed it back together, and he is now president-elect of the
Well done. There's more to come. That's very good. Professor Young, we're going to stay with you. I'm going to ask you the first question that is not related to a joke. And that is that you're very excited about a specific area of neurological research at the moment, and I believe in a recent interview you said that optogenetics was something that was really taking your fancy. Can I get you to expand on that, please?
Yes, optogenetics. This is a word that may sound understandable, but opto is light, and genetics is manipulating genes, and optogenetics is where you can attach a little light-sensitive channel. So a little channel that will open up and ions and other things can cross back and forth across the membrane. So, but it's activated by light. You can put now into the brain by various genetic techniques these channels, and you can put them into, say, I just want them in one particular part of the brain, like the dopamine cells that are affected in Parkinson's disease. They're in a tiny, tiny little area of the brain, but you could put optogenetic channels in that area of the brain, in each dopamine cell, and shine a blue laser light, or whatever color laser light you've hooked to that channel, and it will activate them. So just by, you can take a little animal, for instance, and you can have put these channels in. You have a little fiber, a little optic fiber that goes in, and give them a little blast of blue light, and they will either get up and start walking around, almost as if they had had some L-Dopa, or you can use other channels that will block the cells and stop them from acting. And one of the things that is so amazing about this technique is, for all of us at this table, I think we always wished we could, in fact, activate specific pathways in our brain all at once, so we could see what the behavior of an animal was after you had done that. And previously, we couldn't do that. But with the development of optogenetics, we can now light up whole areas, very specific nerve cells of that group that Dr. Faull was talking about earlier. Now, what is really exciting, I think, is that we all don't want to have little fiber optic, fibers coming out of our head, but now there are also channels that are activated by drugs from plants, okay? So the drug won't act on anything else in your body except on that channel. It's almost like the blue light. But now you can take a pill and activate only those cells that have the little channel that has the sensitivity of that plant drug. I think in the next 5 to 10 years, we will be using that kind of thing in human experimentations, trying to activate pathways in the brain that will make a difference for our ability to move, to have memory, to even affect things like epilepsy and other problems in our brain. So it's a very exciting technique, and I think it's one that is very applicable to human disease.
Very exciting. I'm going to stay with you, and I'd like you, please, to talk about the excitement of finding the Huntington gene. You were a big part of that.
Well, yes, that was some time ago. So actually, Richard Faull and I have spent a lot of our careers working on Huntington's disease, and I was fortunate enough to have met a woman named Nancy Wexler, who herself is at risk for Huntington's disease. Her mother died of it. And when she learned of this back as an early graduate student, she decided to devote her whole life to finding out the gene and hopefully therapies for the disease. And so she put together a team because she had identified a large family in Venezuela living along the shores of a lake called Lake Maracaibo. It's sort of an inland sea, actually. And along the shores of that lake was a family that, after we had been there for a number of years, we realized was huge, a huge family with Huntington's disease. There were 18,000 people in the pedigree, in the family tree. Now, not all 18,000 had Huntington's disease, but there were thousands that carried the gene. And we went down there year after year, starting in 1981, to collect blood samples, skin samples, sperm samples, other samples that would allow us to analyze the family tree, to trace the gene through the family tree and identify the gene that way. It was sort of a primitive time in genetics when the whole human genome hadn't even been attacked yet. It was using the methods that were used for Huntington's that actually allowed us to go forward to map the human genome. And in 1983, 2 years after we began, we localized the gene for Huntington's to the end of chromosome, the short arm of one of our chromosomes, chromosome 4. And then 10 years later, we were actually able to identify the mutation. And the mutation was a very interesting mutation because it was as if your genetic information is like a book of instructions on how to put your body together. And the mutation, that is the defect in the gene, was as if one letter or one word was being repeated over and over again too much. Like supposing you thought something was very good, you might say, oh, that was very, very good. But in this case, it was like, oh, that was very, 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 very good, and you would kind of get lost. Well, that's all it takes to make that gene no longer work normally, and it affects the brain in areas throughout the brain. And Professor Faull has been one of the leading scientists identifying exactly what areas are affected in Huntington's brain and what symptoms you get from those areas that have been affected. So we now can test people for Huntington's disease. We can we've actually got methods whereby we can reduce the Huntington gene in the brain by genetic techniques. And those trials used to be trials that we would only think of, well, actually, I don't think I dreamt of them, to be honest with you, back then, that we would be doing this. But now we're able to do it, and they're in clinical trials now, in humans, in London, Germany, and Canada. And it's going to be a very exciting time to see whether, by lowering the mutant protein in the brain, can you allow those people to live, say, into their 90s with no symptoms of the disease. And we know that can happen. I know it can happen because I've seen patients who are in their 90s who have early Huntington's disease. And Huntington's disease normally affects you in your 30s or 40s. But what happens? Some people, it comes on very late. And that means to us as scientists that if that can happen naturally, then that can also happen in a way that we can probably affect it. So,
thank you. Incredibly exciting. Professor Shaw, you had a similar experience with a couple of families quite a while ago, actually, with a familial motor neuron disease, and that changed your tangent, I guess, into motor neuron disease research. Can you tell us about that experience and what's happened with your work in the last couple of decades since?
Right, okay. So I trained in New Zealand, and actually two things. I'm really, really, really proud to be part of the Centre for Brain Research in Auckland, and I think it's an extraordinary organisation. And I'm even, sorry. Yes, it's on. I'm even more impressed that so many of you think a good night out on a Friday night is to come here and listen to us. So that makes me very proud to be a New Zealander, that people are so involved in research and interested and excited by it. So I trained here as a neurologist, and I went to work in Cambridge, and one of my colleagues hurt his back, and so I ended up doing his clinics out in Bury St Edmunds, and I met a woman who had motor neuron disease, and I made the diagnosis. But she knew exactly what was happening because she'd seen 4 members of her family who'd gone through exactly the same condition. And when it first started, she knew what was coming. And up until that time, I really didn't know that it could be familial. And she then talked to me about the burden that she'd had most of her life waiting for this to happen. And so every time she tripped on a piece of pavement, every time she had trouble turning the key in the door, she thought, is this it? And that struck me as a really unfair disease, firstly, to have this condition. And that you have been anticipating this, it then arrived, and then you thought, hell, I may well have passed this on to my children. So I was very touched by this, and I got to know her and her family very well. And then a month later, I met a woman almost exactly the same position. And I then started to talk to people who were working in the field, and we identified the gene defect in these 2 families, and it was called SOD1. It was a very appropriately named gene. And for a very long time, that was the only gene that was available, and I used to give talks, year after year, sod all so far. But we and others have identified now, I think, 15 credible genes for motor neuron disease. And these have a crossover with a related condition called frontotemporal dementia. And one of those genes turned out to be a really important one in a protein which is deposited in most people with motor neuron disease, and it's a protein called TDP43. So when TDP43 was first identified by pathologists, a really breakthrough discovery, other people in the field rubbished it. In fact, they said this was cellular junk. Some very famous and important people in the field. And we sequenced the gene in our patients, and we found just one family who carried a mutation, which makes you think it probably might not be real, but we really worked very hard to collect an enormous number of people from this family, not quite as big as yours, but we identified that the area that they all shared was the area that contained the gene encoding TDP43. We then did some cellular experiments and showed that the protein misbehaved when it was mutated, and we showed it was toxic in the spinal cord of a chicken embryo. So then we finally believed this was a real result, and we had that published, and then lots of other people had a similar sort of result. And we discovered a number of other genes that relate to that since. And what's most exciting for me is not just the gene discoveries, is that we're now turning those into models in cells and animals where we can try and discover therapies and understand the disease mechanism. And as we speak, in fact, just today, I've submitted a form to a company who are running a gene therapy trial for motor neuron disease, knocking down one of the genes that we helped to make a contribution to discovering. And so when I was writing out this thing and typing it off and sending it off, and why would you be interested in doing this? Well, we discovered the gene. That was a pretty big motivation. And I've seen more families with this than most people on the planet. And I have always wanted to turn those discoveries into a real therapy, and that has happened. So that is an extraordinary place to be. And there are families in New Zealand who carry this gene defect, and I really hope that we will be able to extend those sorts of therapeutic advances to the patients here. That's a great opportunity.
Fabulous. Thanks, Professor Shaw. Richard, I'm going to ask you to explain the relationship between Professor Shaw and this young lady in the photograph behind us, please.
So the person you see there is Emma Scotter, and she was a very bright PhD student who went through the Centre for Brain Research, and very interested in molecular genetics and became interested in motor neuron disease. And so after she graduated, we wanted to send her off to the top lab in the world. And I'd previously met and knew all about Chris, and Mike Draganoff and I said, well, you should go to Chris's lab. And she went off to Chris's lab, and she did postdoctoral research there. So here's a New Zealander going over to work in a New Zealander's lab in London, one of the top leading labs in motor neuron disease. And the feedback we got from Chris is that, there's something special about New Zealanders in science. They seem to identify the problem in a quite straightforward way, and then they just go in a very logical way and say, let's just solve the problem. And over the time, what she was with you for 3, 4 years?
3, 4 years.
Yep. She actually developed, and Chris can give you more details about the precision of exactly the research she did, but she actually developed within Chris's lab a whole branch of looking at the genetics underpinning motor neurone disease. And she was a great team builder in a very quiet, effective way. And she ended up sort of running Chris's lab. And he always says, send me more New Zealanders like her. Well, and then when she came back to Auckland in the Centre for Brain Research, and she was awarded an Aotearoa Fellowship, and she's subsequently been awarded the Rutherford Fellowship because she's doing such critical breaking work in terms of solving the genetics and looking at, we've got human brain cells in our lab from people who have died of motor neurone disease and who wish to have their tissue given to our human brain bank, the Neurological Foundation Douglas Human Brain Bank, to support research. So we were able to do, when Emma came back, work on those human brain cells to apply the knowledge she actually learnt in Chris's lab. Not only that, for a while, she would call up and link up via Skype every Saturday morning with Chris's lab, and she kept running your lab and organising it from New Zealand. I'm here.
So, yeah, she's certainly the smartest postdoctoral scientist I've had in my lab. And one of the best things was she didn't agree with me that often. So we had proper debate. And one of the things when you've got grey hair and you're a professor, people are reluctant to challenge you, but that doesn't seem to be the case with New Zealanders. And I really missed that. So I really missed and lost out since she came back. But what I'm really pleased about is to reconnect with her, and we've got half a dozen really exciting ideas that I think we're going to be able to pursue. And I hope I can keep up with her. She doesn't run my lab anymore, but we're hoping that there's a strong link between our two labs. And actually, within the context of the CBR, there are lots of projects that I'm really excited about and I would like to be more involved in. So that's been part of this week. It's a pleasure for me.
Fabulous. That's very exciting. Speaking of young people, Professor Bartlett, I have a photograph here. I think it's about 30 years old. This was on the eve of the setup, I believe, of the first neuroimmunology lab in the world. Can you describe that time, please?
I have no memory of it whatsoever. Thank God memory goes. I just, this is sort of like, this is your life, isn't it? I'd just come back from a postdoctoral 4 years at Johns Hopkins and then University College, and that was a combination of I was trained in immunology, and then I went and started doing neuroscience, and it was a critical time in neuroscience, and it's a very interesting thing about disciplines, that disciplines are dominated by the hegemony of very few people. So immunology does science a certain way, and neuroscience does science another way, and they're completely and utterly different. So when I went to University College with Martin Raff, who was also an immunologist who turned to neuroscience, we started to apply some of the technology that was immunology, that is to try and use antibodies to identify various parts of the brain, because at that stage we thought there were different types of cells in the brain, but we had no idea how to identify them. So when I was at University College, we made the first monoclonal antibodies, very specific antibodies against subtypes of brain cells, which was the first identification of individual brain cells. So when I came back to Australia, there really wasn't too much molecular neuroscience going on, which was pretty true a lot of places around the world. And so I came back to an immunology institute, which is a very famous one, the Walter and Eliza Hall Institute, where Faull Burnett had founded, who won the Nobel Prize, as many of you know, for transplantation immunology. And I had to set up a lab that had some immunology and some neuroscience to start with. So we set up what was a neuroimmunology lab, and it was the first in the world, and I didn't really know what we were going to do, but I can tell you one thing we did do, which was important. There'd been a long time belief that the brain was different than the rest of the body. And it is different because it's protected by a very strong mechanism that keeps out a lot of viruses and proteins from the blood. It's called a blood-brain barrier. The blood vessels within the brain have tight junctions that don't allow penetration of molecules, as well as the surrounding tissue. And there were many papers published saying this was partly due to the fact that the brain was privileged. That is, the brain didn't respond to foreign tissue like the rest of the body. If you transplanted a piece of tissue from one person to another, obviously you reject it, but it was thought if you put it in the brain, it would stay there forever. And in fact, there were some fairly interesting experiments done, although when you look back, they were terrible experiments. So, taking up Chris's and Richard's point, I mean, one of the interesting things, and I think luckily Australians share the New Zealand sense of not scepticism, but certainly you don't take things as granted just because someone tells you. So we started working on the idea that perhaps the brain wasn't an immune privileged place and that there was really a priori no real reason. The other reason that people thought was that the cells in the brain didn't express these molecules on the outside of the cell, which were called transplantation antigens, which were recognised as what was foreign when you transplanted pieces of tissue between people. So we were able to show in pretty simple experiments that in fact, although they normally didn't express these transplantation antigens, as soon as there was any inflammation or any release of molecules associated with inflammation, they made massive amounts of this, and you could show that the immune system worked perfectly well in the nervous system as it did in the rest of the brain, and it rejected things and it saw viruses. So that was one of the things that came out of that neuroimmunology lab, but I have to say I abandoned the immunology part of it very rapidly from then on in and moved straight into neuroscience.
Well done. From neuroimmunology to pharmacology, Professor Muller, in 1977, you made a discovery of a very special receptor in the brain called the benzodiazepine receptor. How did that shape your work in the following decades?
Well, when a bit like Barry Bartlett, when I had studied chemistry and biochemistry, and that's a sort of a bit of a lifeless science, and I wanted to get into neuroscience and study the brain. And at the time, like in Australia, in Germany, there was no neuroscience at any of the universities. It's hard to imagine today because everybody has now a neuroscience department. So, but I met by accident in a course a colleague from Roche, and they said, well, we are very interested in brain research because our company has developed drugs which can manipulate the brain in the most amazing way. And these drugs were the so-called benzodiazepines, and they were selling them like hotcakes, and they were selling them to put people, like today, people who couldn't go to sleep took a benzodiazepine and they went to sleep and slept and woke up and had mostly no hangover. And if you didn't cope with life properly and got stressed out by situations, either your workload was too high and so on, you would take a benzodiazepine, a so-called anxiolytic, which took away your feeling of anxiety. So you were able to cope with it. You didn't care as much with the situation as you would without the drug. So this was dramatic. And the company made billions, of course, on this. But nobody knew what actually happened in the brain and how this how did all this come about? And the answer was then, and the young biochemists came and they said, why don't you look into this problem? And it was actually, looking back, it was very simple. The drug goes into the brain and binds to a certain receptor, and that's the so-called benzodiazepine receptor. And what it turns on, just about throughout the brain, is all the inhibitory systems, the systems in the brain which dampen the activity. I mean, there's always neurons firing away and others dampen them. And in that balance, the drug helps you to calm down the excitatory events in the brain. That's basically what these drugs do. And later it was found that's exactly this brake system. It actually the brakes in the brain, not the accelerator, the brakes. And what was found that in patients with panic disorders, really people who can't cope with life because the panic is so strong, they have the feeling they're going to die. And that can happen anywhere, in the street, in a restaurant. It's a terrible condition. It was found that exactly that braking system was missing in certain parts of the frontal brain, especially in that area where the decisions are made and values are compared. Is that dangerous or not? What should I do? And so on, from all the stimuli coming in. And that's exactly where the brake was missing. And in patients with post-traumatic stress disorder, veterans coming back from the war, Iraq or Vietnam, the brake system has broken down to an incredible extent. In some of these patients, about 50% of these braking molecules are just gone. The neurons have gone. There are no brakes anymore. And sometimes when you look at these pictures, you think, how can these people cope with life? So that is the connection between the benzodiazepines which were sold at the time. Now, the story, of course, didn't end here because the whole brain is full of these braking systems. It just wasn't imaginable that the same brake system operates throughout the brain. I mean, the brain is so complicated. And there now, and what was found, there are different brake systems, and you can develop different drugs for different brake systems. And that is an era we are still working on, and so now one can develop agents which are actually sleep-inducing, and others which are actually anxiolytic without being sedative. And you can also turn it around. You can say, instead of enhancing the brake, I want to have less brake, so the brain gets a move upwards. And that can be done in particular areas of the brain which are related to learning and memory. And drugs have been developed in animals, which in that area, which is required for learning and memory, take the brake off. And in animals at least, drugs which do that, the animals learn a lot faster and a lot better. And some of these drugs will be tested soon in conditions like Down syndrome and in other probably psychiatric conditions. And one has to see whether there is a way to improve the therapeutic conditions for these diseases. But that's where the science went, from discovering the brain through the drugs. The drugs were actually the tools to find it. And then now to fine-tune the different brake systems, even in the case of learning and memory. So that's
Excellent.
a story.
It's a great story. Your work is described as therapeutic neuroscience. Mm-hmm. So are receptors the common ingredient across all of the areas of your research in disorders such as epilepsy, sleep dysregulation, anxiety, and so on?
Yeah, that is. I mean, epilepsy, in the essential drug list of the WHO, there is Valium, an essential drug. And it is on that list not because of its side effects. It's there because you can stop an epileptic attack. Whatever else happens, if you put high enough a dose of diazepam, the epilepsy will stop. And so in many conditions, you need to enhance the brake or reduce the brake. And the one I worked on was the GABA system, but there are many other receptors which are used. There are drugs the classical drugs used in schizophrenia manipulate basically the receptor for dopamine, largely, or for serotonin. And sometimes you have drugs which do both, manipulate both receptors to have the right balance. And that is actually the trick or the challenge in drug development. Sometimes you don't want just one receptor, because which would be too simple. So you need a drug which acts on two systems, and to find the right balance, so you have a therapeutic effect and minimal side effects. That is actually the art in drug development.
Brilliant. So what's the most exciting aspect of your work at the moment?
Oh, the work on learning and memory, no question. There's a receptor, a subtype of a receptor, which is almost exclusively located in the hippocampus. And without hippocampus, there's no learning and memory. That's just the way it is. And that's where we are trying to manipulate the brake so there is a little less braking activity in order to stimulate the hippocampus and help the learning and memory. It's the area which in Alzheimer's disease is just disappeared. The degeneration in Alzheimer's disease, once it will in the end always affect the hippocampus, and the hippocampus will just degenerate. And then I think we come at the end of drug development at the moment. But nevertheless, the attempt is there to help with learning and memory deficits.
Good. That holds great hope. Richard, can I ask you to explain then what's happening in the hippocampal area in this illustration behind us?
So this is a brain. On the left-hand side is a healthy brain. On the right-hand side is severe Alzheimer's disease. And it's pretty obvious that there's something not going on too well here. And you see what's happened is that down here deep in the, trying to use my pointer but it's not showing where, down here deep in the temporal lobe towards the bottom on the right-hand side, the hippocampus, which Hans just talked a bit about, has actually shrunken enormously. And it has, here we are. Yeah, so here you can see on this right-hand side, it's shrunken enormously. The cortex has also been affected. The brain cells die. And these brain cells which die in Alzheimer's disease, when you go right back to the very earliest stages, we see that there's a specific bad protein which accumulates in the brain which seems to kill these cells, and it's called amyloid. And by the time the person first presents with the symptoms, there's already quite major cell death. And if I can go to the next slide, which I know I just saw, shows the normal brain and the Alzheimer's brain. So this normal brain, you see, this weighs about 1,500 grams in the normal person. Here, we see in the Alzheimer's brain, it's lost at least 1/3. It's of the order of probably 800 to 900 grams. And it starts off in that area, which is the area which is involved with learning and memory, deep down here, entorhinal cortex and hippocampus, which goes first. And then it spreads to involve the other areas of the cortex. And the tragedy is that it sort of marches around the different parts of the brain involved, first with memory, then with personality, and then the other higher complex functions. And ultimately, the person loses their whole personality. They are no longer the person the family knew. And that's the tragedy. Going in at this stage of the disease and trying to turn it around is an impossibility. One of the things we and many other groups around the world are looking at is if we could get in very early in the disease, when the first symptoms, the first hints of the disease appeared, if we could take people at that stage and look at all the factors which make the disease progress, if you could slow it down, that would be great. And we've actually done the figures. In New Zealand right now, there's 60,000 people affected with Alzheimer's disease and dementia. if you could slow down the onset and progression by just 5 years, by different types of therapy, treatment, all sorts of sensory stimulation and so on, different packages looking at the diet and so on, if you could start down by 5 years, you'd actually drop the prevalence of the disease by 50% because people would live longer, more switched on, have a higher quality of life for longer, and they die of a different disease. And so sometimes we always say, well, I'm asked, have you cured the disease first? Well, we want to cure brain disease, but actually slowing down brain disease can actually make a huge impact. And so we're looking at, we've just established special clinics and we're working with groups in Australia to try and see by looking and studying people in the early stages of the disease. We call these the Dementia Prevention Research Clinics. We're gradually establishing across New Zealand if we can actually do that. And that would be marvellous. That would actually give hope to so many people.
Thank you, Professor Faull. You have a resource at the Centre for Brain Research called the Neurological Foundation Douglas Human Brain Bank, and you've collected over the past 22 years, I believe, since 1994, tissue from very generously donated brains. Can you describe the resource, please, from a scientific perspective, and then advise us how this has informed research both in New Zealand and around the world?
Well, this resource is incredible. We could not have planned to do this. In fact, when I came back from the US after doing work at MIT looking at the basal ganglia, the area affecting Huntington's and Parkinson's, I'd done all that work on rats, you see. And I arrived back in Auckland in the early 1980s and started up my own little lab, just myself working on rats. And I was working at this basal ganglia region affected in Huntington's and Parkinson's. And I had the professor of genetics come along to me, and this was in the early 1980s, and this was 13 years before the gene was discovered, this Huntington's gene, which is a tragic gene because it's a dominant gene, and if that gene's in your family, you'll get Huntington's disease. But there's no way to test for it. There were families out there, and Arthur Veal, the professor of genetics, said, I'm looking after all the families in New Zealand, 400 of them, with this disease called Huntington's disease. We can't test and make sure they've exactly got the disease. You can only be a clinical diagnosis until you actually look at the brain after death to really confirm. He said these families need to be helped because some of these symptoms can be highly variable and it can not be, sometimes it's not easy to precisely diagnose it if you don't have especially if you don't have all the family history, which in some cases they didn't. Would you look at the brains of these families? For them, after their mum or dad have died, they'd like you to look at them and say, report back. So we started that. And we started looking at the human brain, and we looked at it in pathology and did detailed studies, and then we'd phone and talk to the families and have an interaction with them, and we would tell them exactly what the results were. Now, the amazing thing was that, well, first, the disappointing thing is that in most cases we actually confirmed they had Huntington's. In a few cases, they didn't. So that was great news. But what these families did, and this is the human side of research, they said, keep the brain and do research on it and see if you can find a cure for our children. Now, that was the beginning of a brain bank. And what they also said is that we want to help you in any way possible. So we would go back to the families and ask them questions. We'd go to the doctors who treat and look after them, get more details on that brain of that person during their life so that we'd better understand the pathology that we saw. And this gave us an insight into Huntington's disease which was totally unexpected. It showed us that all the different cells, not the same cells died in exactly the same way. It varied a lot. It depended on the symptoms and all manner of things, although they may have had the same gene. And it suddenly opened up the complexities of what happens to the human brain and brain disease. Because the families were so interested and so keen to do this, they would register with us and say, we want to get the brain tissue to you as soon as possible. This is what mum or dad wanted. And because we know by having a short time from death till it gets into the lab, makes it more precious for doing gene studies and all the rest of it. So we ended up, you see, with a community of people, first in Huntington's, then Parkinson's, then Alzheimer's, then motor neurone disease, then epilepsy, who wanted to help our research. This is humanity helping drive research. So they sort of said to me, go and work on the human brain. Now, if I'd actually thought, can I collect human brains to work on it, would have been too hard. The ethics would have been impossible. But we actually started doing this before there were ethics committees. And so, when coming into the 1990s, I suddenly realised that we had a resource here. I talked to one of my colleagues and they said, you know, we've actually got a bank of human brain tissue, a human brain bank. I said, let's talk to the Neurological Foundation and see if we could sort of formalise this and make it a research-orientated human brain bank, quite different to the others overseas, because in a small country you can talk to the families a lot easier and talk to the doctors who are just across the road a lot easier than you can in a big city like New York or a big country like the United States or whatever. So we ended up developing this boutique human brain bank. And the Neurological Foundation came on board in 1994 and gave us our first grant, which funded and helped the expenses of that and paid a person and subsequently a research fellow also to look after this incredible resource. And so that's, believe me, a very short version of how our human brain bank got established. It was the community driving us in the most special way, in the most humble way, and I could never have dreamt when I graduated in medicine, someone said, what would be the greatest thing you'd like to do with research on the brain? I couldn't have dreamt of saying, I want to study the human brain and solve the mysteries of what happens in Huntington's, Parkinson's, Alzheimer's, epilepsy, and so on. The great thing about this boutique human brain bank was that we got the tissue soon after death, short post-mortem delays, the shortest has been something like 2 hours, up to 12 to 15 hours. We knew the track record and we go back to the families, we collect all the data. And so we did our different studies on the tissue using special chemical stains and so on. We did the pathology, but we were not experts in every area. And the word got out around different groups who we worked with, and Nan Young and others overseas, that we had this resource. And they said, we would like to use some of your tissue to study genetic changes or other types of protein changes or whatever that we couldn't do, but they could do. They had all the resource, they had the money to do this. So we went to families and said, would you be happy for us to send a little bit of this tissue from your mum's brain, from your dad's brain, to a leading group in Boston, and Oxford, and Zurich, Stockholm? And in every single case, the family said, absolutely, this is a dream come true. You know, Mum is going to get the travel and death she never had in life. And others said, you know, it's like Dad lives forever. And so that humbles you. So we are the custodians of a community drive to drive research on the human brain. The Neurological Foundation, and then we got support through the Neurological Foundation from Sir Graham Douglas and his family trust, so it's called the Neurological Foundation Douglas Human Brain Bank. And we've got something which is quite unique, because you can do things in a small country that's sometimes easier to do than in a big country. And yet we need all our experts. And in fact, the collaborations of these people here that we've got actively going on and others around the world has come out of that. And it's made my life just incredibly exciting. And it's made me humble. And it means we're there for the families. You see, so we have tissue from about 1,000 brains now. We have whole brains. We've had about 600 brains given to us over that period, and they've been very carefully preserved and dissected and kept frozen in a -80 freeze in a special way, which took us years to develop. And we keep in contact with all the families. And the contract is they can come to us and they ring us up anytime. And I've had families ring me on Christmas Day when the families are all together having dinner, and they said, listen, we're just ringing you up, the kids are all here, they want to know how the Huntington's research is going. And you spend 2 hours on the phone. And I come away and say, my gosh, this puts your life in perspective, but also enables us to do research on the human brain, you see. And you can't do research on the human brain, really, normally, but in this way you can. And it gives you access to the most incredible commitment of families to help research, and it's put us on the map. That's why these people are here today, actually. Thank you.
Brilliant. Thank you, Professor Faull. Professor Young, I think it's time for a joke. Yeah. I've got one.
Oh, go ahead.
This was sent to me earlier in the week, and it's very, very well timed, actually, because when doing my research for this panel discussion this evening, I came across a 30-year-old story called Brainy Women, which was in the Harvard Gazette, I think it was back then, and Professor Young was one of these amazing brainy women. And in the New Zealand Herald this week, in the Sideswipe column, I'll read that to you because I understand it will be a bit difficult to read. To whom it may concern, I understand that Miss Marjorie Rain is applying for a position as assistant in a bacteriological laboratory. I have pleasure in supporting that application. I have known Miss Rain for 3 years and supervised her practical work in chemistry during 2 of those years, 1 year in the first year laboratory and 1 year in the advanced laboratories. Her chemical laboratory work was distinctly above the average, and she showed initiative and resource beyond the standard usually expected from a woman student. Her general capability, I have observed, and so he goes on, and this was sent in, this young woman found it in her mother's belongings, so I think that's perfect. And the face of neurological research is certainly changing, and Professor Young, I'll get you to comment on that, please.
Comment on...
Young women coming out to neurological research.
Young women doing neurologic research. When I decided to become a neurologist, just like the others here, there weren't neuroscience departments. You went and worked with somebody who might have some interest in neuroscience. But in my class, medical school class, there were 110 students and 9 women. And that was pretty standard. So there weren't many women doing research. And there were very few women going into neurology. And I wondered about that, actually, because it is a wonderful, wonderful subspecialty. You not only get to take care of some of the most difficult illnesses in medicine, but in your early years, or when I was young, you couldn't do much for those illnesses. But the one thing that you could do is try to help the family get through each stage of the illness in the most comfortable way that was possible. And that was something that women actually, I think, do well with. And yet, very few women went into it. And I wondered, well, is it because women are afraid of the nervous system? And no, that wasn't entirely true, I didn't think, after talking to people. It actually turned out that some of it was due to the way we examined brains back then. When I trained in neurology, there were no CT scans. There were no brain scans. You got to get an X-ray of the brain, or you could do something really horrible, like what was called a pneumoencephalogram, or an angiogram, where you shot dye into the arteries and then lit up the arteries in the brain. Now, back then, nowadays, when you shoot dye into the brain, you put a little catheter in your groin and feed it up into the vessels that go up into your brain. But back then, the neurologist stuck the needle right in the carotid artery. And because there were no CT scans and no other kinds of scans, like PET scans, you often did this in patients who had terrible head injuries and other things, and so you had them, strapped down to the table, people holding on, the person was agitated, and you're trying to hit this vessel, and women didn't like that, actually. So that, I think, in many ways, put people away from neurology, but I think it's actually the perfect subspecialty for women because you get to take care of people long term. You get to, most neurologic diseases nowadays, the things that have happened in the past 40 years since I trained in neurology, it's different now. We can treat diseases. We have, in the next generations of young students that are coming along, there are going to be new therapies for Huntington's, for Alzheimer's, for Parkinson's, all of these things, motor neuron disease. The generations that are starting now in graduate school and medical school are going to be able to do this. And there are going to be men and they are going to be women. And it's a great subspecialty. I can tell you some funny things that happened to me as a medical student. One was that all the men, to keep the lecturers, who were mostly men, in order to keep the medical students happy, used to show nude women and Playboy pinups and cartoons of nude women and you name it. And the 9 of us would sit there and go, oh boy, this is like getting boring. But one day I decided I'd get back. And I asked a friend of mine in the pathology department, it was back in the very early 70s, and I got him to get me go down to the red light district of Baltimore. I was at Hopkins doing my degrees, and get a full frontal nudity picture of a man on a cliff, all greased up and muscular. And this guy who had been showing all these Playboy pinups, I noticed that he put his slide carousel in the machine before lunch and then would come back after lunch for the lecture. So I slipped my little slide in, and when he came to the slide, there was this shock of horror on his face, and he went immediately to the next slide. And all the guys in the class said, hey, wait, Dr. So-and-so, back it up for the women. They want to see this. And they never showed another Playboy pinup again. So.
Thank you, Professor Young. Look, we've talked about genes and proteins. Professor Bartlett, I'm going to ask specifically about stem cell research now and how over the last 3 decades things have changed specifically in this area, and it's beginning to inform now the prospect of some really hopeful treatments for brain disease. Can you talk about this, please?
Yeah, well, following on from my neuroimmunology lab, it gave me that sense of trying to look at different subpopulations in the brain. And one of those ideas was to be able to identify the cells that gave rise to these billions of neurons that Richard talked about. So we developed methods to be able to study growing these developing neurons in the tissue culture, and we found methods of making them divide, and we realized that there were a few cells in the developing brain that could divide and give rise to many, many thousands of neurons. And again, with my Australian, New Zealand skeptical sense, I said, well, why wouldn't they still be in the adult brain? That is, stem cells have that capacity continuing to keep self-renewal. Therefore, if we can grow them from the young developing animal, why can't we grow them from the adult? And of course, at that stage, it was thought that making new nerve cells in the adult brain was something you couldn't do. It was all downhill once you were born. And sure enough, we were able to show that in the adult mouse brain, there were cells that you could stimulate using this technology to make new nerve cells. So that was 25 years ago. So it's taken us 25 years to work out what the use of these things might be. And it's very, what I'll concentrate on is, although we worked in other areas to start with, the hippocampus, as Hans and Richard have said, is the most important part in terms of learning and memory, in terms of encoding all the sensory information and making sense of when and where things happened. And all these memories that tend to perhaps fade in older populations. But let me cut to the chase. In older animals, as in older humans, the production of these new nerve cells, which occurs normally, slows down. And in fact, in mice, by about 12 to 18 months, the production in the hippocampus, which is one of the rare areas where this occurs, almost ceases. The good news is it looks that in humans that isn't so precipitous, it slows down. Now, in old mice, just like some of our older population, not all, of course, this is not irrevocably linked as you get old, that you do suffer disease. There are plenty of brains, there's 120 that have been looked, 115 have been looked at that look pretty normal. So we've been looking in animals to try and reverse this slowdown. The good news is the cells that make these new nerve cells are still there. They're reduced a little bit, but there's a lot of them still there. You don't need many. So we've been looking at ways of reversing that decline in these old animals and seeing if we can reverse these memory loss. And the good news is we can. So in recent studies, one of the best ways of activating the production of these new nerve cells in these old animals is to give them exercise. So we've been looking at what precise, because I know you're all going to ask me what sort of exercise should I do. And so we've been looking at this in old animals. Now it's been known for a while that young animals, you only need to exercise them for a little while, but it turns out, now this is, you've got to keep this secret because it's not published as yet. It turns out in old animals, you've got to run them for a precise period of time. And that period of time for mice is 5 weeks. The good news is, if you run any longer than 5 weeks, it's just as bad as running less than 5 weeks. So there's a sweet spot of exercise that activates the production of these new nerve cells. And that sweet spot corresponds to the improvement in cognitive ability. So not only can you slow it down, Richard, you can reverse this cognitive loss. So we're just about to start, we have started, we've enrolled about 200 people between the ages of 65 and 85, where we're doing deep examination of circuitry using very high-powered MRI, looking at the epigenetics, looking at the blood chemistry, because we think we know what molecules are regulating in this, and these are the ones that will be the biomarkers, to see if we can find that same sweet spot in humans. Because the literature is full of tantalizing data that say exercise is good for your brain, but tell me what it is, So, and I said the good news is that too much exercise mightn't be any good at all. So, I'm hoping that hangs true. So in 18 months' time, we should be able to come back, if you invite us back again, and I'll be able to tell you exactly what form of exercise to do. But I think it's, dementia / Alzheimer's, of course, what percentage of dementia really is Alzheimer is becoming more and more difficult to perhaps quantify. Many people say perhaps it's only 25% of older dementia might be pure Alzheimer's. So I think some dementia in the older population, in the 1 in 3 people over 85 who suffer some functional loss might largely be due to certainly hippocampal misfunction, but some of that may well be reversible given appropriate stimulation, whether it be exercise or it be drug therapy. So I think more and more, I'm a lot more optimistic, Richard, than, of course with gross pathology, as you show, this is not going to work, but I think in the large number of people it is going to show. I mean, there are some interesting statistics coming out from the Framingham studies about the incidence of dementia in these various cohorts since the 1950s, and the last cohort is showing a 40% reduction from the 1950s. Now, why that is very difficult to know. One of the leads, because there's not much else difference, and the reduction only occurs in people who have been educated to a higher level. So we've always known that level of education somehow lowers your risk of dementia, but we're sort of the chicken and egg.
Yeah.
But it may be, given that we have got a much more educated population, that in fact it does drive some so-called increase in cognitive reserve, whatever that may be. I hate the word. The other thing is that weight's increased. Now, here's something naughty, because all the public health people are going to jump all over me. But there's been another study published, which you probably saw in the Lancet Diabetology, which looked at 2 million people who were looked at body mass indexes in their 40s and 50s, and then looked at the incidence of dementia. And surprisingly, that the incidence of dementia was inversely related to obesity. That is, the morbidly obese people had the lowest incidence of dementia, thin people had the highest. So now, I know. So this is 2 million people. This is not a small study, but this has been greeted with absolute silence. And but there is some science behind this. Fat cells make some interesting molecules. One of those is leptin. And leptin, it turns out, is a very strong stimulator of neurogenesis. And we're just doing those studies now to see if leptin... So we've always known that a bit of weight in older people has a lower incidence of dementia, but that's always been thought that people, as they get dementia, lose weight. But it may be keep a bit of weight on. Quite a lot of weight on, I think. But don't tell the public health.
Professor Bartlett, I'm going to stay with you and talk about the Queensland Brain Institute at the University of Queensland that you helped to establish in 2002. What was your mission when you set the institute up, and what have you achieved in that time?
Well, exactly the same as Richard. I mean, I had the fortune to be invited to go and set up an institute, which sort of doesn't happen very often, especially when there's a fair amount of money involved. And so you get the chance of saying, what should you do? And I took the line that, as Richard mentioned, that until we understand how the brain function works, how could we ever cure disease? Because essentially all brain diseases are a misfunction of circuitry. That is, the connections between cells that encode memory, function, the way you walk, the way you think. All these are circuits that in some ways are damage or dysfunction in any of these diseases, whether it be psychiatric or it be neurological. So understanding how the circuitry encodes memory, how it regulates behaviour and function is fundamental to us ever finding ways of solving those questions. So I was fortunate that we were able to recruit large numbers of people who just focused on trying to understand, using everything from honeybees through fruit flies, through C. elegans, flatworms, to humans and mice and rats, to try and dissect how the function of the brain is regulated. And that's taken a fair whack of time. And I think in many, just like us, many people around the world are now starting to apply that deep function Anne talked about, whereby we are starting to be able to regulate circuitry. We're able to show and monitor the response of circuitry to behaviour and to chemicals. So we really are entering a golden age whereby we are going to be able to manipulate the circuitry directly and understand directly what the circuitry that underpins these defects. So what we're missing now is just some things that work.
Thank you. Professor Faull, last night you celebrated 7 years of the Centre for Brain Research, and which began with 25 labs, I believe, and somewhere close to 100 researchers.
Yeah, we've actually got we've got 71 research groups now involved, and we add all not only the leading researchers but the postdocs, the PhD students, and the graduate students. And the professional research staff. It's about 450 people, which is incredible. We never realised there's so much brain research going on in Auckland University in all the different pockets until we started saying, let's all talk to one another and collaborate. And 7 years ago, we started off with the 25 groups we thought were sort of doing this. And then as we developed and as we talked and worked more closely with the neurologists and neurosurgeons, we started to develop a really humming area of collaborative research. And then all other groups started coming out from the psychology department, from even in arts, people looking at the effects of dance on dementia and so on. And all these people said, can we join this club? People like to work together as teams, and especially in a small country, to capitalise on the investment in research, the more you can work as teams involving both researchers, both clinicians, work in the hospitals, looking after people with brain disease, and then talking to one another, interacting and linking out to the community and the schools, you can suddenly create a little tidal wave of effective research. And that's sort of what we've got going in a way. And I could not have dreamed. I probably would have run a mile if I knew what was going to happen. But it's so incredibly exciting. And the great thing is, though, the early and mid-career researchers across our centre, and this is typical, I think, for any centre, the potential which they have, the enthusiasm, the commitment, and neuroscience research is really complicated now. We've got all these fancy tools. You've got to get bright young minds. Well, we've got lots of bright young minds, and they run fast, and they talk to one another, they collaborate, and they help drive the whole program. So we're pretty proud of where we are, Sue, but where we're going to go is going to be even more exciting, and that's just incredible.
Great.
I'll just ask you to explain this diagram, because this is a very big part of the work of Associate Professor Bronwyn Connor and her lab, and this is exciting for brain research, isn't it?
Yeah, and this is, just very briefly, this is where you can take, it's incredible that the stem cells that Perry was talking about, these are cells that can go and become whatever they want to become, given the right circumstances. And these stem cells are just so versatile, and they are precious, and we're going to develop new therapies through them. What's amazing, and people around the world, and we've got people like Bronwyn Connor in our Centre for Brain Research showing that you can actually take a mature cell from the skin, take it, grow it in the lab, and then put certain genes into it which tell that cell, hey, you may be old, but I'm going to turn you back to the young stem cell. And then you can start seeing how you can take those cells from that patient and then tell it to go into and make cells which may help that person to get over a disease. That's a very general overview of it. There are all sorts of challenges, and there are lots of debate about how effective this is going to be and all the rest of it. But this is suddenly turning our brain research, in fact all research on the human body, upside down. And it's exciting, so that cells in our body, brain or any other tissue, they are continuously changing. We think that, they're static, that what's a brain cell now is a brain cell forever, what's a skin cell, but there is continuous change, second by second, minute by minute, in the cells in your brain, the cells in your body, but in the brain, depending on the impulses they get to, that feed into that cell, will depend on how that cell continues to function. It can send out little new processes, get more input. It can atrophy down because it's not getting input. You can add new inputs and you can change it. And this was heresy. I would have been shot at dawn 10 years ago if I'd said that. And this and the sort of work which is going on in terms of how genes control cells and motor neurone disease that Chris is talking about, absolutely cutting edge stuff. And we're going to be able to develop new technologies using this and other techniques which give us hope to help people with brain disease. That's very general.
Brilliant, thank you. We're close on time. I've got one question for each of you, and then we'll go to a public question and answer session. Professor Bartlett, I'm going to start with you because I'll get you to carry on the theme that you were discussing before. Should we, in inverted commas, use it or lose it?
Well, I think that's a pretty good saying. I mean, there's no doubt that, as Richard said, that making new nerve cells is an exciting way. But you know, for those cells to actually function when they're made, they've got to integrate into the circuitry. And it appears, the golden rule to get survival of these new nerve cells, as it is during development, that they need to make functional connections. And functional connections means that there is stimulation, there is information flow between the nerve cells, and if that doesn't occur, those cells die. And at a lesser extent, if those cells aren't stimulated, they also tend, as Richard has just said, that the number of connections or the number of very small synapses that they make is also reduced. So use it or lose it is at many levels. One is survival of neurons, the other is keeping the number of connections between nerve cells where the information is coded is just as important as well. So yeah, there's no doubt. I mean, the question is, what is the best stimulation for using it? And I mean, there is a lot of data from animals that says, obviously, exploration, a very enriched environment. For humans, as I've just said, education, people who learn languages, explore the world, continue to sort of have different impulses, different sensory information coming into the brain. So, you know, I think we've got to get a lot better at knowing exactly what forms of stimulation. I mean, there are people who are out there, I won't name this person, who say, she's Dame something, who say that, you know, too much visual information is bad for our children. Well, I've never seen any scientific data that says that. But so there's a lot of anecdotal to and froing going on here about, you know, kids are watching too much digital TV. I don't know if that's true or not. I suspect it's not. I think they're getting visual information that's stimulatory. So we're still very early days of understanding what is the best form of stimulation, especially for an ageing population. It's certainly not in a nursing home, unless that nursing home has got a lot of activities and things that drive these stimulations. But in general, what you said, use it or lose it, is correct.
Great, thank you. Professor Muller.
Mm-hmm.
Some researchers say that the great paradox of studying the brain is that the more that we learn, the less we know. Do you agree?
Well, it's a nice saying, like the previous one. It's a similar saying. We've learned in the last 10 years more than the last 1,000 years about the brain. It doesn't mean anything to me, these sort of comparisons. And of course, we have different technologies, and that's why we know more or other things about the brain than the generation before, obviously. For me, the question is, what do we do with that? And there are technological advances and stem cell reprogramming and so on. The question is, what do we do with it? And how can we develop new therapies? And there we chose an organ, the brain, which is just very complicated. But I'll give you an example that medicine can overcome enormous obstacles. 30 years ago, everybody was afraid of HIV/AIDS becoming an epidemic, and nothing could be done about it. The immune system just collapsed, and people died. And it was basic science which, broke the spell. So we found out it was a special virus, it's a retrovirus, and then it was found out again by basic science that this virus uses a machinery which is different from the human machinery in certain ways. And those brought targets for drugs, and today AIDS is a manageable chronic disease. You can look at it that way. So there are enormous progress. And what the example of HIV/AIDS shows, you have to know the cause, you have to know the machinery, how the pathology develops, and then you can develop a drug. And in brain research, we just don't know the cause. We don't even know the cause of Parkinson's disease. We just know that it happens, and we know what happens. And in Alzheimer's disease, the good old Alzheimer, if you ever come to Munich, go by the Institute of Psychiatry, and you can still see the slices, the brain slices the old Alois Alzheimer actually did. And today, we don't know a lot more. Not the cause, we know not much more about what happens in the pathology. So I always use this this example of HIV/AIDS. It was the basic science which finally broke the spell, and that will happen here too.
Incidentally, this year it's 200 years since James Parkinson described the shaking palsy. Interesting. Professor Young, I'm going to come to you now and ask what you believe is going to be a big breakthrough in movement disorders in the next 10 years.
Well, I think, first of all, I would like to say I kind of disagree with you.
Okay.
In that I think that, for instance, you were saying about ALS. There are many genes for ALS now. For Parkinson's disease, there are 25 at least different genes that can cause Parkinson's disease. Every single gene that you have is that could cause Parkinson's, is a possible drug target for stopping it. And so if you know about the details of the genes and how the various genes fit into the circuits and pathways, you can start to manipulate them and at least begin to understand how these diseases start to affect the circuits. It's true we don't know exactly how they're caused right now, the fundamental underlying cause, but we know so much more than we knew just 10 years ago. And we can manipulate those pathways and circuits, and we can find drugs for them. And you're the master of doing that. So I think that in basal ganglia research, right now there are things like, for Parkinson's, deep brain stimulation, other technologies. I think we're going to be going well beyond those and be able to manipulate things better. But I think the underlying real pressure for us as scientists is delaying the onset of the disease. And we know we can do that in animals. We can give animals all of those diseases. We can put every single one of the genes for Parkinson's into a mouse, or for Alzheimer's into a mouse, or for ALS into a mouse. And we know that those mice will develop a disease very similar to a human disease. Not identical, but with the human gene in the mouse. And we also know that with genetic, you can grow those animals up, they'll get symptomatic, And if you turn that gene off in the middle of it, the animals get better. It isn't that it stops. The animals actually improve. If that's the case in the laboratory, again, we ought to be doing that in man, and it's going to happen. I am a total optimist on this. And I think with the kind of thing that Richard has put together here in New Zealand, I want to emphasize as somebody who's not from New Zealand, just what a special thing he has done here. He has put together things in New Zealand that have not been possible anywhere else in the world, and he shares it with people. And the patients and their families share it with the world. And this is the most important thing for science to collaborate across the world and not become isolationists like our government is trying to do now. And we should not let that happen. So.
Thank you very much. Professor Shaw, your question is, you study familial disease. What about the other aspect of non-familial motor neuron disease and the different various aspects of that kind of research work providing hope for the future?
Sure. So we started off with familial disease because there was a clear, strong genetic component to the condition in those families. But every single gene we've discovered in those families is also appearing in people who have no family history at all. And in fact, if you look at all the people who've got disease and all the genes, there are more people who've got no family history at all that carry those genes than do have a family history. So that's bad in a way, in the sense that there is a risk of inheritance in those families that didn't know it existed before. But actually, it's really hopeful as well, because those mutations are very ancient, and that means that there have been many generations in which people were protected. So that tells me that there are mechanisms within those individuals and the families that lived a normal lifespan without getting disease that meant that they somehow could stop the disease happening. So they carried the gene, often they were making an abnormal mutant protein throughout life, but they had the machinery in their neurons to protect them. So we're trying to figure out exactly what that machinery is and how to enhance that. And ultimately, obviously, we will be treating people who have the condition, but we want to find the people who are at genetic risk of having it and give them the drugs before they even manifest. So that's where I want to get to, and if I get... we're getting pretty close to it, and I'm pretty confident that's going to happen in my working lifetime. But fortunately, I know that there's a whole cohort of really clever young people, including in the Centre for Brain Research, who will pick up the baton and take that forward as well. So that's the really exciting thing.
Very exciting. And are you going to come home?
Tricky question.
Thank you.
I'm certainly spending a lot of time.
Get the contract out.
Yeah. Thank you. Professor Faull, I've got the last question of the evening for you, and I know everyone will be very interested in the answer to this. Do you think that we are going to be able to one day soon stop Alzheimer's disease in its tracks, or slow down the progression of Parkinson's disease, or perhaps prevent stroke altogether?
Well, I would like to say yes to all of that, but you know, when you look right now, there's no single brain disease that we can absolutely cure. So I just want to follow up what Anne says in a way, slowing progression, identifying risk factors that make the disease go faster, offers the biggest opportunity right now. And part of that is stimulating your brain, part of that is looking at all the factors which predispose a person to Alzheimer's disease, and then trying to go through in a logical way and eliminate that, and that involves multifactorial aspects. In areas like motor neuron disease, which Chris is the expert in, identifying genes, then we've got a target you can go to, and you can do that. And genetic engineering and churning genes down is going to offer a lot of hope. But what we do know is that, for example, in Huntington's disease, you can't just go in and turn the gene off, because the gene actually does some good things and that would be lethal. So there's a balance in all this, and so we're not going to solve brain disease overnight, but we can help by looking at all the things that go in a very complicated way to the progression of the disease and see if we can knock off one of those at a time. There's going to be magic gene therapy can come in different ways. And you learn a lot from one disease that you can apply in another disease. We're learning a lot from Huntington's, it's caused by a single gene, to help us, if we can fight that and turn that gene down, it's going to help the multi-gene disease like Parkinson's. And the same comes from motor neurone disease. Single genes cause different types of motor neurone and so on. So it's not a straightforward question that we're going to be able to solve these diseases, but we're going to help people, and we're going to be able to give them more years of higher quality. And that is hope. And it means getting the message out there. It means communicating with the community and making sure we keep them involved with the research, tell them what's going on, involving and working with clinicians who are seeing patients on a daily basis, and they know what's realistic and what's not. So it's all about team. Can I just say one other thing, which I must do with these people here today who've come from literally all around the world. You know, one of the great features of brain research, and it's about all science really, is that we progress forward by standing on the shoulders of giants. And that's teamwork in lots of ways. And I just want to give you one example. I could say all of these 4 people here tonight, they're giants. They're not here by accident. We in Auckland, at our Centre for Brain Research and our brain, we've interacted with these people in different ways. And I just want to give you one example to show that. Now you see, in the 1980s, when we started getting and looking at the brains of people who died with Huntington's disease, we had this precious tissue to try and solve this disease. And we were looking at the pathology of it, but we started looking at the chemicals too. And there's pharmacologists who are at the university. There's Ken Taylor sitting up there, and there's John Villiger, who introduced me to new techniques to look at the chemicals, because we knew there were chemical imbalances in Huntington's. And in the early 1980s, there was a paper came out by 2 people I'd never heard of before, called Anne Young and Jack Penny. And they showed, quite interestingly, that a particular type of receptor was changed in a very interesting way, lost in one part, increased in another. And those receptors were the benzodiazepine receptors. So we had this human tissue, and I thought, we've got to look at these receptors. And we did use the same techniques that Anne had used, what we call receptor autoradiography, which gave us a sort of a global picture of the changes. We want to get a specific antibody to attach to these receptors so that we could look at it under the microscope and do lots of more detailed studies. And I was talking to Ken Taylor, and because a paper came out in 1985 by a guy by the name of Hans Muller. And he was in Basel, worked at Hoffmann Roche in Basel. And as he was telling you, they had a real interest in these benzodiazepine GABA receptors. And he published a paper in Nature with his colleagues saying, we have just made antibodies to 3 of the different subunits of this receptor. So I was talking to Ken, who'd actually gone, and he's working for Roche in Auckland. Well, he's the #1 guy there, actually. And I said, Ken, this guy, Roche in Basel, is there somehow we could get hold of some of those antibodies? And Ken said, well, actually, you know, I know Hans. He's married to a New Zealander. And, you know, New Zealanders stick together. And so Ken wrote off to Hans, got a letter back from Hans. And what transpired was that he gave us a secret supply of these antibodies, which were enormously expensive to produce, is what we call monoclonal antibodies, each of the subunits of the GABA-A benzodiazepine receptor. And we put them on our human brain. He didn't have human brain. He had lots of mice and rat brains, but he didn't have any human brain. So we were able to apply that, to the human brain. And out of that, over 20 years, we developed, and we've used his antibodies to not only look at what's going on in Huntington's, but Parkinson's, Alzheimer's, and we've been able to do this on multiple levels. We've been able to show changes that occur in the human brain. In the Huntington's disease one, interesting features this is used, we've found is that we have been able to identify the very earliest changes in the Huntington's brain. So we have ended up, in fact, got support from the Freemasons to take the human gene for Huntington's and put it in the sheep, and we did it in Australia, and made a whole line of sheep over there. This is starting about 10 years ago, which are now being used today, and we can see that they're like Huntington's in the early stages, and it's now being used today to test drugs. And this is a group in Massachusetts working on our sheep in Australia to see if they can turn the gene down. Now you see, this is standing on the shoulders of giants. So these are the giants, and I've actually just climbed on the top of that. So piggyback. And this is the excitement of science. It's called working together. It's called bringing the expertise together and making a difference, where no one actually owns the knowledge, but the knowledge is owned by the people who actually have the disease who we want to help. And that's what it's all about. And that's why these people, I could tell the same sort of variation of the story as to why we have a scientific advisory board which consists of not only these people, but a couple more who had to go back to Australia and elsewhere today, who would have been here. That science is about working in teams, helping people is about working together, but we're doing it because of people who are affected by the disease, and actually they end up, as I described with the human brain bank, they actually end up driving the disease. And the great thing is we have organisations like the Neurological Foundation who actually collect the money from the community to help fund this and push us in ways which will make a difference. And other organisations which work in all sorts of ways, the Freemasons and so on, which come on board, and the philanthropists which are critical. And it happens in every country. Chris, it happens in the UK just like that, doesn't it? Yep. In Switzerland, Hans, there, United States and Australia. Yep. Well, this guy, he's what he has raised over $100 million in Queensland to set up this Queensland Brain Institute. And he's an example. But so this is what science is all about. Thank you.
Richard will say a few words at the end, but first we'll go to questions.
May I digress a bit and display my ignorance? Is there a part of the brain called the laughing center, the center for laughing? All of us have indulged in that. Can a functional MRI show where the laughing starts? Especially because, not just because we are laughing, it's a normal thing, there's a type of rare epilepsy called galactic epilepsy. So, apropos that, can you please tell me if there is a laughing center? Thank you.
Who wants this one?
A neurologist. Okay.
I'm not sure I know the laughing center, but obviously the tumours that can cause galactic epilepsy usually rise at the bottom of the third ventricle. So there are probably regions in there. I'm not sure there's a specific one part of the brain that's involved in laughing. I doubt that very much, but that's certainly something that can be triggered. So I think the epileptic form of galactic epilepsy, the person doesn't experience pleasure from the laughing. It's a reflexive movement. So I think it's distinct.
Thank you.
And there's also, I can just say there's something called pseudobulbar affect, where patients with diseases will laugh uncontrollably and cry uncontrollably at times that aren't really appropriate. But I don't know where that's localized.
That's frontal disinhibition.
Yeah.
Okay, thank you. Alex.
Hi there. This is something of a general question for all of you, but what role do you think epigenetics is likely to play in our understanding of brain function and disease in the future?
So it's a bit like when you're in the Himalayas and you've just climbed a very big mountain, which is called the genome, and then you discover there's an even bigger mountain, which is the epigenome. And we've made huge advances in terms of understanding the sort of the base elements of our genetic code, and all the other elements that regulate that. But in fact, the epigenome is a really new part of science to discover the influence of. And what's extraordinary about it is that this is the part of the genome which is influenced by our environment. Not only just the environment that you've experienced as an individual, but the environment of your parents as well. When you've inherited those chromosomes, some of their environmental experience is imprinted on the chromosomes that you receive. That is completely heretical from a few years ago. So I think that everything we do now will be judged through a filter of epigenetics subsequently. So I think this is just the beginning. And there are probably more mountains we haven't even seen yet. So we need to keep fit.
Thank you, Natalia.
Thank you for that. That was really inspiring and very interesting to hear about what's going on. I read a little bit about neuroplasticity, and I'd like to know what we can expect in research in that area and how maybe that will influence treatment and research with regards to some of the conditions you've spoken about this evening.
Well, it is a term that's become very, very popular. In its strict neuroscientific sense, it usually refers to the connections between nerve cells, synaptic plasticity, this ability, Richard said, that connections between nerve cells can change and do change on a minute level, both in terms of the chemicals transferred, but even anatomically you can show changes in the forms of these connections literally in minutes. So that's often what neuroscientists talk about in synaptic plasticity. But plasticity, so there's an enormous amount of this going on. As you're listening to me, you're making changes in your, hopefully you are, making changes in many of these connections. So that is, given that each neuron has 10,000 other neurons connecting with it, you can think about the enormity of that information change and flow. Something that still don't understand, how all that information that comes into a neuron is interpreted and encodes functions and memories. An enormously much larger question than understanding the genome. But at another level, it also says that because we can change the connectivity so easily, that if you lose function in one part of the nervous system, the cortex has this ability. There are a lot more connections in the cortex than you're aware of because they're usually inhibited. But under certain circumstances, if you disinhibit these pathways by blocking some of these GABA-type receptors, you can show that there are connections there already that can take over some of those functions lost, perhaps through injury or stroke or something like that. So rehabilitation is what we talk about when we start to use this ability for some of this circuitry to take over functions that it normally was not doing. So it's not that you're making new connections in terms of pathways, you're actually using existing connections but were normally not functioning. So that's another level of synaptic plasticity. In fact, which was discovered many years ago and hasn't actually been worked on all that much, the systemic synaptic plasticity. I mean, another level is what I've talked about in terms of making new nerve cells as well. The fact that we now know in the adult brain you can, in certain areas, luckily like the hippocampus, make new nerve cells that can integrate. So there are lots of different levels of plasticity, but the bottom line is that there is this enormity to change functional control, which we're really just starting to explore. And we haven't been able to explore it terribly well because we hadn't had the mechanisms to look at all these circuitries in detail. But as Anne said, we now have ways to look at these circuitries and stimulate these circuitries and look at their behaviour and how they can change and how they can take on other functions. So this whole field of rehabilitation, which has been a bit of a black box, is still a black box to a large degree, but we're starting to understand that a lot of that's due to this ability to make new connections, reinforce connections, or reveal old connections that hadn't been used, as well as integrating new neurons into the circuitry. So it's an area that, this area of rehabilitation and neuroscience have not been terribly well connected. And bringing those together to understand how rehabilitation occurs after stroke, occurs after spinal cord injury or any other injury, is one of those new frontiers that I think we're going to understand a lot better over the next 5 years.
Thank you. Good question. Thank you. Alex.
Hi, Professor Faull. Is the Liggins Institute collaborating with the Neurological Foundation in the area of gut microbes and the way that it is affecting epigenetics, or just in general? Because I went to a great talk on Wednesday with the Liggins, and they were speaking about microbiota affecting the brain.
Wow, how much time we got? So one of the most fascinating developments which has happened over recent years is the demonstration that your gut flora, as well as what you eat, have a huge impact on brain function. If I'd said that 5 years ago, I would have been laughed at, very far from my job and all the rest of that. Perhaps I should have been. But anyway, the interesting thing is there's a lot of truth in that. And it's developing a lot of momentum. When you think about it, the whole body works together. And why we should think the brain is sitting up there in isolation, and any disease or dysfunction of it happens just purely because of the brain, and not because of some unhealthy aspects of the rest of the body. It's stupid, isn't it, to think the brain system, and that's exactly what this research has shown. It's very strong and powerful research. So the flora and the activity going on inside your gut affects the food, all sorts of things. It actually affects gene function. And we know, we sort of touched on here in different ways, how we said there's 40-odd thousand genes and they all do different things. But what the fascinating thing and the most exciting thing coming out of genes over recent years is the fact that all of these genes are modulated up and down, and they don't work by themselves. They are modulated by proteins which are made by genes, which are affected by the environment and all manner of things, and that at any point in time, the genes in your body are changing and they're affected in an epigenetic way, in a very complex way that make genetics now incredibly complicated. The good old days of Mendel, when you just had a very straightforward view of genetics, was very simple. Now it's got so complex that we suddenly realise it's not just genes that affect who you are and what you are. They do, but they are modulated and changed on a basis, on a daily basis, on what you do, your environment, in ways we're just beginning to understand. And the rest of your body affects how your brain health is. So I haven't really answered your question. I've just told you that, yes, brain health is actually more complicated than what we thought. It's fascinating, and it's opened up avenues of how you can manipulate your health in all different ways, by changing your environment, by how you think about your disease, what you eat and how your gut, and how different types of problems in other parts of the body, if you've got an infection, that will affect the brain health. That will affect a person's symptoms with Alzheimer's disease as to whether or not they have an infection. So we've got a job that's going to go forever. And so, thank you.
Yeah, this is why establishing a neuroimmunology lab 40 years ago was a bit premature, because the gut drives the immune system. The gut lymphoid tissue is where most of the immune cells lay, and it's where most of them are stimulated in terms of their repertoire of what they respond to. And of course, one of the biggest areas in brain pathology and controversial areas is about the neuroinflammatory basis of diseases like Alzheimer's. And there's no doubt that the gut flora influences your repertoire of immune cells that seems to also impact on the resident immune cells in the brain, which are called microglia. So the immune system is all tied up, it's really regulated by the gut flora to a large degree. So we've known about this for a long, long time, that gut flora is very important, but I guess what we didn't know was how susceptible the brain was to inflammatory, immune-based inflammatory conditions. But again, this is still a very controversial area, and the mechanisms by which this occurs is still not clear.
Thank you. Professor Young, have you got something you'd like to add? No. Okay, thank you. Natalia, last question, I think. Thank you.
Thank you. Mine's kind of on a similar note, actually, but I couldn't forgive myself if I didn't thank the panel, because I'm a psychiatrist and I work with schizophrenia predominantly. And when we're working with patients that are suffering every day, we need to see that there are people out there trying to find things to change this for our patients. So it brings me a lot of hope. So that's fantastic. But the question I really wanted to ask was about infective causes of psychiatric illness. And I think you've largely answered it, but I'm just wondering whether the Centre for Brain Research is doing work on potentially infective and then downstream inflammatory causes of schizophrenia and similar illnesses.
I'd love to tell you right now that we've got a team on that, but we don't. But there's a lot of interest in inflammation, there's a lot of interest in schizophrenia. We're bringing these disciplines together in ways which we wouldn't have done normally, which we didn't have the mechanism to do. So we are going to be looking at this sort of thing. We're going to pursue it. It's a new horizon, and it's where neuroscience and psychiatry and mental health and all come together in complex ways. And that's a very complicated subject, but we know that they all intertwine, and the brain's getting more complex as we go on, but we're not going to let that prevent us from doing research on it. So we will be pursuing that, I can promise you. Thank you.
I think Professor Faull is being very modest here, because one of the things that he has made major contributions to in Huntington's disease is, as you know, many patients with Huntington's have psychiatric disorders. And there are others who don't. And he has been able to show in postmortem human brain the differences between those patients who have psychiatric problems and those patients who do not, and which nerve cells are affected, and which pathways are affected. So yes, he has a team. It is working on it. And I'm sure those contributions are going to grow as your brain bank grows, wouldn't you say?
Absolutely.
Yeah.
Thank you. Ladies and gentlemen, before I hand the floor over to Richard to say farewell and thank you, I would like to thank all of the panellists on behalf of the Neurological Foundation. I have been truly honoured to sit with you this evening and ask questions that I know everyone was very keen to hear the answers on. It has been an honour to see the interest as well this week at all of the lectures and the talks, and I know that the 4 visitors have inspired a lot of young people for sure in the talks this week as well. Professor Faull, thank you very much for partnering us once more. It has been an absolutely exciting journey to watch how the interest in neurological research has seen the tickets go so quickly for this evening, and another really, really good attendance, so thank you. Professor Bartlett, we look forward to having you back on our cooler shores sometime soon. Professor Young, thank you so much. We look forward to hopefully a nice trip to Boston for a visit. Thank you. Professor Shaw, lovely to have you home, and we look forward to your regular visits. And Professor Muller, who has a New Zealand connection, a New Zealand wife, we'll see you again very soon.
I have to come.
But Thank you so much, all of you.